Code with Confidence, a practical guide to test-driven development. 1. The quest for confident code. Why software development needs a new approach. Imagine, for a moment, that you are building something complex. Not just a house or a car, but something intricate, with thousands of interlocking parts, all designed to work in harmony. Perhaps a sophisticated clockwork mechanism or an advanced piece of biomedical equipment. As you assemble it, you need to know, with absolute certainty, that each component functions perfectly, and that when combined, the entire system will perform exactly as intended. What if, after days, weeks, or even months of painstaking construction, you flip a switch or wind a spring and nothing? Or worse, it malfunctions in a subtle, unpredictable way, causing a cascade of errors. This is, in essence, the daily reality for software developers. We build intricate systems out of abstract concepts, lines of code that interact in myriad ways. Each application, each website, each piece of software is a complex machine, and just like that biomedical device, a small flaw in one component can have widespread, disastrous consequences. Bugs, defects, errors, call them what you will, are the bane of every developer's existence. They lead to frustration, lost productivity, financial losses, and perhaps most damagingly, a gnawing lack of confidence. Think about it. How often have you or someone you know felt that sinking feeling after making a change to a piece of software? That whisper of doubt. Did I break something? Will this new feature accidentally disable an old one? Is this seemingly trivial change going to unleash a critical bug in production? This isn't just paranoia, it's a rational fear born from experience. Traditional software development often involves coding a feature, then later, after it's built, trying to find all the ways it might break. This approach is reactive, often inefficient, and profoundly impacts confidence. This is precisely where test-driven development, or TDD, steps in. TDD isn't just another form of testing. It's a fundamental shift in how we approach the entire development process. It flips the traditional model on its head, suggesting a different, more proactive way to build code. Write tests before you write the code that makes them pass. At first glance, this might seem counterintuitive, even a little odd. Why would you try to test something that doesn't even exist yet? Isn't that like trying to test a car that hasn't been designed or manufactured? Yet this seemingly strange practice is at the heart of TDD, and it unlocks a surprising array of benefits that go far beyond merely catching bugs. Beyond bug hunting, the deeper promise of TDD. While TDD certainly helps prevent defects, its most profound impact lies elsewhere. TDD is, at its core, a design practice. It's a tool that helps developers craft cleaner, more modular, and more maintainable code. Consider an architect designing a building. Would they just start laying bricks, hoping for the best, and then later try to figure out if the structure is sound? No, they would meticulously plan, draw blueprints, and consider every stress and strain before construction even begins. In software, these blueprints are often a little fuzzy, evolving as we build. TDD acts as a kind of constant, real-time blueprint refinement process. By writing a test first, you're forced to think about how you want to use the code you're about to write. You're asking, what should this component do? How should it behave when given specific inputs? What are its explicit responsibilities? This initial act of defining the desired behavior through a test clarifies your intent. It acts as a clear, concise specification for the tiny piece of code you're about to create. This clarity helps you avoid over-engineering, keeping your code focused and simple qualities often referred to as KISS. Keep it simple, stupid, and YHNI, you ain't gonna need it. If you can't easily test a piece of functionality, it's often a sign that its design is flawed, too complex, or too tightly coupled. TDD doesn't just catch bugs. It helps you design in a way that prevents them from ever being written in the first place, by compelling you to build modular, testable units. The problem with traditional development. A crisis of confidence. Let's delve a little deeper into why traditional approaches fall short and why this lack of confidence is so prevalent. The build first, test later, trap. In this common scenario, developers build a new feature, often in isolation, and then hand it over to a separate quality assurance team for testing. This creates a disconnect. The developer's primary goal becomes make it work, not necessarily make it right or make it maintainable. Bugs are found late in the cycle, leading to costly rework and delays. It's like finding out your car's engine has a fundamental design flaw after the entire car has been assembled and painted. Fear of change, the fragile code syndrome. Many software systems, over time, become fragile. Making a change in one area might inadvertently break functionality in another, seemingly unrelated, part of the system. This leads to a creeping fear of touching legacy code. Developers become hesitant to refactor, reluctant to improve the design, and even afraid to implement new features, because the risk of breaking existing functionality is too high. This stifles innovation and leads to stagnant, unmaintainable systems. Slow feedback loops. Imagine you're trying to tune a guitar, but you only hear the sound 5 minutes after you pluck a string. It would be incredibly difficult, wouldn't it? Similarly, in traditional development, the feedback loop from making a change to discovering a bug can be painfully long. Weeks can pass between a developer writing code, integrating it, deploying it, and then having a user report a bug. This makes debugging a frustrating archaeological dig rather than a quick surgical strike. Documentation debt. Code bases can often become black boxes. Without clear, up-to-date documentation, new team members struggle to understand how things work. While TDD isn't a replacement for documentation, well-written tests serve as living examples of how the code is intended to be used, providing invaluable context and clarity. This cycle of fear, slow feedback, and reactive bug fixing creates a challenging environment. It leads to developer burnout, missed deadlines, and ultimately, less reliable software for users. The path forward. Embracing a new rhythm. This book is your guide to adopting a new, more confident way of building software, a way that leverages the power of test-driven development. We'll explore how TDD isn't just about creating tests, but about cultivating a disciplined approach to development that constantly focuses on clear thinking, intentional design, and rapid feedback. We'll peel back the layers of TDD, starting with its core, rhythmic cycle that will become second nature to you. We'll examine how this cycle subtly but powerfully influences your code's architecture, making it more robust and adaptable. We'll look at how TDD builds a safety net around your changes, transforming the fear of refactoring into a confident stride. And crucially, we'll explore how these principles apply to the complex, imperfect reality of everyday development, including tackling the daunting challenge of legacy code. You don't need to be a seasoned testing expert or a programming language guru to embark on this journey. This book focuses on the mindset and practice of TDD, not the specifics of any particular programming language or tool. Our goal is to equip you with the conceptual understanding and practical wisdom to integrate TDD into your own work, regardless of your current technical stack. By the end of this journey, you will not only understand TDD, but also possess the tools to transform your development process. You will build software with greater confidence, knowing that your code is not just working, but truly robust, well-designed, and ready to evolve. Your quest for confident code begins now. 2. Unmasking TDD, more than just testing. When people first encounter the term test-driven development, their minds often jump straight to testing. And that's a completely understandable leap. After all, test is right there in the name. But to truly grasp the power and purpose of TDD, we need to shed this narrow perception. TDD is not merely an exercise in writing more tests. It's a profound shift in how you think about and how you build software. As we discussed in the previous chapter, the quest for confident code isn't just about finding bugs after they've been introduced. It's about preventing them, about designing robust systems, and about maintaining a continuous state of certainty about your software's behavior. TDD is the discipline that facilitates this. So if TDD isn't just about testing, what exactly is it? TDD as a design discipline. Imagine an architect creating plans for a house. Before the first shovel hits the ground, the architect draws detailed blueprints. These aren't just pretty pictures. They are precise specifications for how every part of the house should function. They define the size of rooms, the placement of doors and windows, the load-bearing capacity of walls. They are, in essence, a series of tests that the eventual physical structure must pass. Will this wall support the roof? Will 8 people fit comfortably in this dining room? TDD operates on a similar principle. When you write a test before you write the actual code, you are effectively drawing a tiny blueprint for a very specific piece of functionality. You are defining, in executable terms, what a small unit of your software should do. This isn't primarily about verifying existing code. It's about specifying the desired behavior of code that doesn't yet exist. This seemingly backward approach has a transformative effect on your design process. Clarity of purpose. You're forced to articulate, what exactly is this piece of code supposed to accomplish? If you can't write a clear test for it, you probably don't fully understand what you're trying to build, or the task is too large and needs to be broken down. External perspective. Writing tests first encourages you to think about your code from the perspective of a consumer or user of that code. How will other parts of the system interact with it? This leads to cleaner, more intuitive application programming interfaces, or APIs. An API is essentially the set of rules and instructions that dictate how different software components communicate with each other. If it's hard to test, it's probably hard to use. Modularity and isolation. For a piece of code to be easily testable, it generally needs to be small, focused, and have clear boundaries. It needs to do one thing and do that one thing well. TDD intrinsically encourages you to break down large problems into smaller, manageable units, each with its own specific responsibility. This leads to highly modular code, which is easier to understand, maintain, and replace. Reduced complexity. Because you're constantly thinking about how to test the code, you're naturally inclined to keep it simple. Extra complexity often makes code harder to test, so TDD acts as a natural deterrent to overengineering. So, while the outcome of TDD is a suite of automated tests, the primary benefit during development is improved design. It's a systematic approach to asking, how will I know this works? Before building it, which guides the construction itself towards elegant solutions. TDD is an executable specification. Let's take another angle. Think of a recipe for baking. It specifies the ingredients and the precise steps to combine them. If followed correctly, you expect a certain result, a delicious cake. In TDD, the test you write first acts as a highly precise, executable specification. It states, unmistakably, given these inputs, this piece of code must produce this exact output or behave in this exact way. It's like a micro-contract. Every time that test runs successfully, it proves that the code adheres to that specific contractual obligation. Unlike traditional prose documentation, which can become outdated or ambiguous, an executable specification is always current. If the behavior changes, the test will break, immediately signaling that the specification is no longer met. This provides incredible clarity and precision about your system's capabilities. It's a living, breathing form of documentation that never lies. The fast feedback loop, a developer's best friend. One of the most immediate and tangible benefits of TDD is the speed of feedback. In traditional development, the loop from writing code to discovering a bug can be excruciatingly slow. You might write a feature, compile it, deploy it, manually test it, then wait for someone else to use it and report an issue. This can take minutes, hours, or even days. With TDD, the feedback loop is compressed to mere seconds. You write a small test, you run it, and immediately you know if the tiny piece of code you just wrote works exactly as intended. This instant gratification is a powerful motivator. It allows you to catch mistakes early. The earlier a defect is found, the cheaper and easier it is to fix. A bug caught within seconds of writing, the code is trivial to rectify compared to one discovered by a customer in production. Stay focused. The rapid feedback loop helps you stay in the flow. Instead of getting sidetracked by long debugging sessions, you get quick confirmation, allowing you to move swiftly to the next small piece of functionality. Build confidence. Each passing test is a small victory, a confirmation that you're building correctly. This accumulates into a powerful sense of confidence in your product and your own abilities. TDDVs. Other forms of testing. It's crucial to understand that TDD primarily focuses on unit testing. A unit test verifies the smallest possible isolated piece of code, a function, a method, a class, in isolation. It doesn't typically involve databases, external services, or user interfaces. This is different from integration tests, which verify that different components of your system work together correctly, e.g., your application interacting with a database. Functional system tests, which verify the entire application behaves as expected from a user's perspective. User acceptance tests, UAT, which involve end users verifying the software meets their business requirements. All these forms of testing are valuable and necessary. TDD doesn't replace them, rather, it complements them. TDD ensures the foundational building blocks, units, are sound, making it easier to construct and integrate larger systems. Imagine building a wall. Unit tests verify each brick is perfectly formed and strong. Integration tests verify that the mortar holding them together works. Functional tests ensure the entire wall stands up as part of the house. Thinking of TDD as just testing is akin to thinking a chef's recipe is just cooking. A recipe isn't just about the act of cooking. It's a carefully designed plan, a precise set of instructions, and a guarantee of a specific outcome. Similarly, TDD is a meticulously planned, disciplined approach that ensures software is designed for quality from the very first line of code. In the next chapter, we'll dive into the practical rhythm of TDD, the 3 simple steps that form its core cycle. Red-Green-Refactor. Once you understand this rhythm, you'll begin to unlock the true potential of building confident code. 3. The RGR rhythm, your new software symphony, Red-Green-Refactor. Every discipline, every craft, every intricate dance has a fundamental rhythm, a repetitive sequence of actions that, when mastered, unlocks grace and efficiency. In software development, test-driven development provides just such a rhythm. It's a compelling, iterative dance between defining, implementing, and refining. Once you internalize this rhythm, it will transform how you build software, making it a more deliberate, confident, and even artistic process. This rhythm is often referred to as the Red-Green-Refactor cycle. It's a simple, 3-step cadence that you'll repeat countless times throughout your development day. Each cycle is purposefully short, often lasting just a few minutes, sometimes even less. The power comes from the disciplined, rapid repetition of these tiny steps. Let's break down each beat of this simple, yet profound, software symphony. Beat 1, read the failing test, the specification. The first beat of our rhythm is red. This is where you begin your TDD journey for any new piece of functionality, no matter how small. What it means, you write a very small automated test for a behavior that does not yet exist. When you run this test, it must fail. Why it's red? It's red because the corresponding functionality hasn't been implemented yet, or the existing implementation doesn't correctly support the new behavior you're describing. Think of a traffic light turning red. It's a clear signal to stop, to acknowledge that something isn't ready. The purpose, defining the specification. This is where TDD truly shines as a design discipline. By writing the test first, you are concretely defining what you expect your code to do. You're thinking from the perspective of how your code will be used, rather than how it will be built. This forces clarity of thought and helps you design clean interfaces. Proving the test. Crucially, a failing test ensures that your test itself is valid. If you wrote a test that passed right away, how would you know it's actually testing anything useful? Perhaps it's just badly written, or the functionality already exists, and you didn't need to write it. A red test confirms that you have not yet satisfied the desired behavior, and that your test suite is capable of detecting when you do. Smallest step first. You write just enough of a test to describe the next tiny, discrete piece of behavior you want to add. Don't write a test for the entire feature at once. Break it down into the absolute smallest increment. Imagine you're building a feature that calculates the price of an item with sales tax. Your first red test might simply be, when I calculate the price of a known item, the simple tax calculation should result in a specific, expected output. You run it. It fails because the tax calculation logic doesn't exist yet. Perfect. Beat 2, green making it pass, the simplest implementation. Once you have a single, failing test, you move to the second beat, green. What it means, you write the absolute minimum amount of production code necessary to make that previously failing test pass. Why it's green? The traffic light turns green, signifying that you can proceed. Your test is now satisfied, and the desired behavior has been implemented. The purpose, Focus on functionality. The goal here is singularly to make the test pass. This often means writing code that feels almost too simple or even a bit clumsy. You might hardcode a value or write a conditional statement that feels incomplete. The key is to avoid writing any more code than is strictly necessary. Avoid over-engineering. This step actively prevents you from building more than you need at the moment. If a more general or elegant solution comes to mind, resist the urge to implement it now. Your only concern is getting to green. Rapid progress. This constraint helps you move quickly. You're not trying to write perfect code, you're trying to meet the very specific demand of a single test. This keeps your momentum high and your focus sharp. Following our tax example. To make that first tax calculation test pass, you might hardcode the tax rate or even the final result for that specific item. It feels wrong, but it makes the test pass. Now your test suite is green again. Beat 3. Refactor, cleaning it up, the improvement. With your tests all green, you arrive at the third beat. Refactor. This is where the magic of TDD's safety net truly shines. What it means. You improve the design of your newly written code, or existing code, without changing its external behavior. Why it's safe? Because all your tests are currently passing, you have a living, breathing safety net. As long as the tests continue to pass after your refactoring, you have a high degree of confidence that you haven't introduced any regressions or broken any existing functionality. The purpose? Improve design. This is where you turn that simplest possible, or clumsy code from the green, phase into well-structured, readable, and maintainable production code. You might eliminate duplication, extract smaller methods, improve naming, or reorganize classes. Eliminate duplication. Often, in the pursuit of making a test green quickly, you might introduce some redundancy. The refactoring step is where you identify and remove this duplication, making your code base leaner and cleaner. Enhance readability. Good code is readable code. Refactoring is an ongoing process of clarifying intent, simplifying complex logic, and making it easier for yourself and others to understand later on. In our tax example, having hard-coded the tax rate might feel inelegant. Now, in the refactor step, you might extract that hard-coded value into a constant or load it from a configuration, making the code more flexible and readable. You run your tests after each small refactoring step to ensure they all stay green. The symphony of confidence. The beauty of the Red-Green-Refactor cycle lies in its meticulous, controlled nature. Red gives you clarity. It forces you to think about what you want to achieve before you build it. Green gives you functionality. It ensures you're delivering behavior, not just architecture. Refactor gives you quality. It allows you to continuously improve the internal structure of your code without fear, confident that your actions are not breaking existing functionality. Each turn of the cycle is a tiny victory, a confirmation that you're moving forward in a disciplined, safe way. This continuous feedback builds immense confidence. You're never in doubt about whether your changes are working because your tests are constantly telling you. This allows you to be much bolder in your refactoring and simpler in your design, knowing that a comprehensive suite of tests has your back. This rhythmic flow becomes second nature with practice. You'll find yourself performing these Red-Green-Refactor cycles automatically, almost unconsciously, for every small feature, every bug fix, and every improvement you implement. It's not about writing tests. It's about adopting a conscious, structured way of thinking through problems and building solutions. Now that we understand the rhythm, let's delve deeper into how TDD, through this very rhythm, fundamentally shapes the design of your software. 4. Beyond bugs, how TDD shapes superior design. In the previous chapter, we danced through the captivating rhythm of Red-Green-Refactor, the 3 foundational beats of test-driven development. While the immediate outcome of these cycles is working code accompanied by passing tests, the true power of this process extends far beyond mere bug prevention. It subtly, yet profoundly, influences the very structure and quality of your software. TDD is not just a testing technique. It is a powerful design tool, forcing you to think about how your code performs its duties before you even write the first line of its implementation. Many developers, when they first encounter TDD, see it primarily as a means to catch errors earlier. While it unquestionably excels at this, reducing bugs is merely a beneficial side effect. The core benefit, the truly transformative aspect of TDD, is its ability to drive superior software design. The testable metric, a compass for good design. Think about what makes a piece of code easy to test. Generally, these characteristics include small and focused. A unit that's being tested needs to be small enough to isolate. This encourages methods and classes to have a single responsibility. Independent. A unit should ideally not depend heavily on external factors, like databases, network calls, or complex global state, for its core functionality. If it does, those dependencies need to be easily replaceable for testing purposes. Clear inputs and outputs. It should be obvious what goes into the unit and what comes out. Deterministic. Given the same inputs, the unit should always produce the same outputs. Side effects and random behavior make testing extremely difficult. When you write tests first, for a unit that doesn't yet exist, you are intrinsically encouraged, no, forced, to design your code with these characteristics in mind. You're asking, how can I make this piece of functionality easy to prove it works? The answer to that question invariably leads to better design. How TDD nudges you towards good design principles. Let's explore some key software design principles and how TDD naturally nudges you towards them. Single Responsibility Principle, SRP. This principle states that a class or module should have one, and only one, reason to change. TDD inherently supports SRP because when you write a test, you're usually testing a single, specific behavior. If your test begins to describe multiple, unrelated behaviors, it's a strong hint that the unit you're about to build is trying to do too much. You'll find yourself naturally breaking down complex tasks into smaller, more focused units, each with its own set of tests. This results in smaller, more cohesive classes and methods, which are immensely easier to understand, maintain, and reuse. Analogy: imagine testing a Swiss Army knife. To test the knife blade, you don't also test the corkscrew and the screwdriver at the same time. You test each tool. Independently, TDD encourages you to design single-purpose tools. Loose coupling. Loosely coupled components have minimal dependencies on one another. Changes to one don't significantly impact others. TDD helps achieve this because, to test a unit in isolation, you often need to mock or stub its dependencies. This practice of replacing real dependencies with controlled test versions highlights areas where components are too tightly intertwined. If it's difficult to replace a dependency for testing, it's a strong indicator that your components are too tightly coupled, and therefore less flexible and harder to change. Analogy: think of Lego bricks. They connect together cleanly, but you can easily snap them apart. You can test a single brick's color or shape without needing the entire Lego castle attached. Tight coupling is like gluing the bricks together. High cohesion. Cohesion refers to the degree to which the elements inside a module belong together. High cohesion suggests that a module's responsibilities are closely related and internally consistent. TDD promotes high cohesion by making you focus on narrow behaviors. If a test implicitly requires a class to perform many unrelated actions to satisfy a single test case, it signals low cohesion. Analogy: a highly cohesive team has members all working towards a single, clear objective. A low cohesion team has members who are all trying to do very different, unrelated things. Clarity and intent. Writing a test first forces you to confront the intended behavior of your code. This act of defining what a piece of code should do, before you worry about how it does it, brings immense clarity. It helps you articulate the precise responsibility of a method or object. If you struggle to write a clear test for a feature, it's often a sign that the feature itself isn't well understood or that its boundaries are fuzzy. Emergent design. TDD champions an emergent design approach. Instead of spending weeks or months upfront designing a vast, complex architecture, which often changes once real coding begins anyway, TDD encourages you to design incrementally. You build up your system piece by small piece, guided by the executable specifications of your tests. The design emerges organically from the needs of the features you are implementing. This allows the design to be flexible and adapt to changing requirements in a way that rigid upfront designs often cannot. Analogy: it's like building with Lego bricks without a preset instruction manual. You start with a small idea, build a few interconnected pieces, and as you do, a larger, more coherent structure organically emerges, driven by the immediate functional needs. You ain't gonna need it. YAGNI and simplicity. The red-green-refactor cycle, specifically the green phase where you write just enough code to make the test pass, is a natural antidote to over-engineering. It discourages adding features or complexity that aren't immediately required by a passing test. This helps you keep your code minimal and focused on current needs, reducing unnecessary complexity and potential bugs. The tests as living documentation. Beyond acting as design drivers, the tests themselves become a form of living documentation. They clearly demonstrate how individual units of your code are meant to be used, what inputs they expect, and what outputs or side effects they produce. A new developer joining a TDD-enabled project can look at the tests to quickly understand the intended behavior of a component, rather than sifting through outdated documents or trying to reverse engineer complex logic. This documentation is always accurate because if the behavior of the code changes, the tests will break, alerting you to update them. Unlike written prose that often becomes stale, your TDD tests are a precise, executable specification of your system's current behavior. From fear to freedom, the confidence of design. Ultimately, TDD transforms the act of software development from a potentially fearful activity. Will my changes break something? Is my design sound? To one of deliberate, confident design. The feedback from the tests is continuous, guiding every design decision. This constant validation frees you to refactor aggressively, to explore new design choices, and to adapt to changing requirements, safe in the knowledge that your tests are guarding against regressions. By embracing TDD, you're not just writing better tests. You're writing better code, building better systems, and becoming a more confident, capable developer. The quest for confident code is intrinsically linked to the quest for superior design, and TDD is the most powerful tool in your arsenal to achieve both. In the next chapter, we'll explore even more deeply how this safety net of tests can act as your code's guardian angel. 5. The safety net. TDD as your code's guardian angel. Imagine you're a trapeze artist. What allows you to perform death-defying aerial maneuvers with such grace and confidence? Of course, it's incredible skill, years of practice, and trust in your partners. But there's another critical element, the safety net stretched tautly below. That net, though rarely used, transforms a terrifying feat into a breathtaking performance. It allows the artist to push boundaries, to try new movements, and to recover from unexpected slips, knowing that catastrophic failure is unlikely. In the world of software development, test-driven development provides precisely this kind of safety net. We've discussed how TDD drives better design and clearer specifications. Now let's explore perhaps its most comforting and enduring benefit, the profound sense of safety and confidence it instills, turning fear into freedom. Fear of change. A developer's common nemesis. One of the most persistent anxieties in software development is the fear of change. This fear manifests in several ways. Refactoring hesitation. Developers often shy away from improving the internal structure of their code, refactoring, because they worry about introducing new bugs. A poorly named variable, a convoluted loop, or a duplicated block of code might be an eyesore, but if it's working, the perceived risk of touching it often outweighs the benefit of improvement. This leads to accumulating technical debt, a growing pile of messy code that slows down future development. Feature creep anxiety. Adding new features to an existing, untested codebase can feel like walking through a minefield. You implement the new functionality, but in doing so, you might unknowingly break an older, existing feature that was never comprehensively tested. Bug fix paralysis. Even fixing a simple bug can be nerve-wracking. A one-line fix in one part of the system might cause an unexpected regression elsewhere. This fear is rational. Without a robust and reliable mechanism to verify that changes haven't introduced regressions, every alteration becomes a gamble. The result is often code that is less clean, less optimal, and harder to maintain than it should be, simply because developers are too scared to touch it. Your automated safety net. The comprehensive suite of unit tests built through the TDD process acts as your automated safety net. Each test verifies a tiny, specific piece of your system's behavior. When you run your entire test suite, typically with a single command, you get immediate confirmation. All green. Your system is still working as expected, despite the changes you just made. Proceed with confidence. A test turns red, something broke. But because your tests are small and focused, you know exactly what broke and where it broke. This pinpoints the problem instantly, turning what could be a frustrating debugging session into a quick, targeted fix. This instant, reliable feedback is the cornerstone of the safety net concept. It empowers you to refactor with confidence. This is arguably the most significant benefit. You can aggressively clean up your code, improve its design, simplify complex logic, and remove duplication, knowing that if you inadvertently break something, your tests will immediately scream at you. This freedom to refactor means your codebase stays healthy, adaptable, and a pleasure to work with, rather than devolving into a tangled mess of technical debt. It turns maintenance from a chore into a continuous improvement process. Analogy. Imagine a sculptor who can instantly undo any chisel stroke. They would be much more daring and experimental, wouldn't they? TDD gives you that undo button for your code. Add new features safely. When you add a new piece of functionality using TDD, you write new tests for it. But crucially, you also run all your existing tests. If any of the old tests fail, you know that your new feature has introduced a regression. This allows you to integrate new functionality seamlessly and confidently, without the constant worry of unexpected side effects on existing behavior. Debug more efficiently. While TDD aims to prevent bugs, some inevitably slip through, especially at higher levels of integration. When you discover a bug in a TDD-enabled system, your first step is often to write a new test that specifically reproduces that bug. This bug reproduction test will fail. Once you fix the bug, the test will pass, and it will remain in your test suite, ensuring that this particular bug never reappears. This effectively turns a bug fix into a new feature, the absence of the bug, that is now permanently guarded by a test. Onboard new team members faster. A comprehensive suite of TDD-driven tests acts as executable documentation. For a new team member, exploring the tests quickly reveals how different parts of the system are supposed to behave. This is far more reliable than outdated written documentation and provides a clear path to understanding the codebase. Enable continuous delivery. The confidence provided by a strong test suite is fundamental to modern development practices like continuous delivery and continuous deployment. These practices rely on automating the build, test, and deployment process. Without a reliable automated safety net provided by TDD, pushing code to production multiple times a day would be extraordinarily risky. The cost of the net, a short-term investment for long-term gain. Newcomers to TDD sometimes perceive it as slowing them down because of the overhead of writing tests first. But I could have just written the code already, they might think. This is analogous to a trapeze artist complaining about the time it takes to set up the safety net. Yes, there's an initial investment. You spend a little more time upfront defining, testing, and refining each small piece of functionality. However, this small investment pays massive dividends in the long run. Reduced debugging time. Bugs are caught early when they are cheapest to fix. Faster development cycle. Because you can refactor confidently and add features without fear, your overall development speed, especially for complex or long-lived projects, significantly increases. You spend less time navigating technical debt and more time building. Higher quality code. The code itself is better designed, more robust, and easier to maintain. Increase developer morale. Working on a code base with a comprehensive safety net greatly reduces stress and frustration. Developers can focus on creative problem-solving rather than constantly worrying about invisible breakages. The safety net isn't just for falls, it's for daring leaps. TDD provides developers with the courage to make those leaps, to explore new designs, and to deliver more reliable software with consistent confidence. Having explored the philosophical underpinnings and the powerful benefits of TDD, it's time to get a little more practical. In the next chapter, we'll discuss the initial setup required to begin your TDD journey, focusing on the conceptual framework rather than specific tools. 6. Your first steps. Setting up for TDD success conceptually. You've learned about the Red-Green-Refactor rhythm, understood how TDD shapes superior design, and embraced the power of its safety net. Now you're eager to start. But where do you begin? While this book deliberately avoids diving deep into specific programming languages or testing frameworks, setting up for TDD success does involve a few conceptual requirements that are universal, regardless of your chosen tools. Think of it less like acquiring a specific brand of hammer and more like understanding that you'll need a hammer, a set of nails, and a piece of wood. The specifics come later, but the principles remain. 1. A language and a testing framework. This might seem obvious, but it's foundational. To practice TDD, you need a programming language. Any modern programming language that can build real-world applications will work. The principles of TDD are language agnostic. Whether you're using Python, Java, C#, JavaScript, Ruby, Go, or something else entirely, the Red-Green-Refactor cycle remains the same. A unit testing framework. This is where the magic happens for automating your tests. Every popular programming language has at least one, often several, robust unit testing frameworks. These frameworks provide the basic capabilities to define tests, a structure for writing test cases, e.g., specific functions or methods marked as tests. Assertions, ways to check if an expected outcome matches an actual outcome, e.g., assert equals, expected, actual, assert true condition. These are the fundamental truth tellers of your tests. Test runner, a mechanism to execute your tests and report the results, usually in a human-readable format, like green for pass, red for fail. You don't need to be an expert in your chosen framework from day one, but familiarity with its basic assertions and how to run tests will be crucial. Remember, the focus here is the concept of having a framework that allows you to write and run tests rapidly. 2. Rapid feedback loop, the heartbeat of TDD. This is paramount. TDD thrives on immediate feedback. If running your tests takes more than a few seconds, the rhythm will be broken and the benefits will diminish. Fast test execution. Your chosen setup must allow you to run your unit tests very quickly. This usually means in-memory operations. Tests should not hit databases, make network calls, or perform any slow I/O operations unless it's an integration test clearly defined as such. Unit tests should operate entirely in memory. Isolated environments. Each test should ideally run independently and not interfere with other tests. Optimized test runners. Modern test runners are often optimized to only rerun tests related to changed code, further speeding up the process. If your test suite takes a minute or more to run, it discourages you from running them frequently. The goal is to run them after almost every small change, sometimes even a few times per minute. Think of it as hitting save, you shouldn't hesitate. 3. Isolation through test doubles, conceptually. As we alluded to in Chapter 4, a key aspect of unit testing is isolating the unit under test from its external dependencies. This ensures that when a test fails, you know the problem lies within the code you're currently testing, not in some other part of the system or an external service. This isolation is achieved through the conceptual use of test doubles. These are generic terms for objects that stand in for real dependencies during a test. We'll delve deeper into the specifics of test doubles like mocks and stubs in the next chapter, but for now, understand the concept. The problem, your price calculator, might need to fetch tax rates from an external tax service or save calculations to a database. During unit testing, you don't want to actually hit that external service or database because it would make your tests slow, unreliable, what if the service is down, and dependent on external factors. The solution? You replace the real tax service or database connection with a simplified dummy version that you control within your test. This dummy object provides canned responses or simply records that it was called, allowing your unit test to run quickly and deterministically. This concept of separating a unit's core logic from its dependencies is crucial for fast, reliable unit tests. Even if you're not explicitly using a mocking framework yet, understanding that your code needs to be structured in a way that allows for these replacements is essential. 4. A mindset for small, iterative steps. While not a technical setup, this is perhaps the most important conceptual prerequisite for TDD. Embrace smallness. TDD demands that you work in incredibly small steps. Write a test for a single, tiny behavior. Make it pass with the minimum amount of code. Refactor. Then repeat. This iterative process is the engine of TDD. Focus on behavior, not implementation. When writing that first red test, don't think about how you're going to code the solution. Instead, think about what should this code do, and how will I know it's done? The how comes later in the green phase. Discipline to follow the rhythm. It's tempting, especially for experienced developers, to skip the red phase or the refactor phase. Resist this temptation. The full benefits of TDD only emerge when you commit to the entire Red-Green-Refactor cycle. Each step plays a vital role. Getting started, a conceptual checklist. Before you write your first TDD-driven line of code, ask yourself, do I have a language and a unit testing framework chosen and conceptually understood? You don't need to be an expert, just know how to write a basic test and run it. Can I run my tests in a matter of seconds, ideally less than 1 second? If not, investigate how to achieve this with your chosen setup. Do I understand the concept of isolating my code from external dependencies for testing purposes? Even if you don't know the tools yet, grasp the why. Am I ready to embrace working in small, disciplined, iterative steps? If the answers to these are conceptually, yes, you are ready to begin your TDD journey. The beauty of TDD is that it's not about complex tools or esoteric knowledge. It's about a simple, disciplined process applied consistently. In the next chapter, we will expand on the concept of isolating code for testing, exploring test doubles, and how they allow you to test your logic in isolation without external interference. This is crucial for maintaining the rapid feedback loop that makes TDD so effective. 7. Testing the unseen, handling dependencies with test doubles. In our journey through test-driven development, we've emphasized the twin pillars of speed and isolation. Unit tests, the bedrock of TDD, must run rapidly and reliably. For this to happen, each test needs to focus solely on the unit under test, without getting tangled up in external complexities. But what happens when your unit, say, a function that calculates a loyalty discount, needs to interact with something outside its immediate control? Perhaps it needs to fetch a customer's loyalty tier from a database or connect to an external service to validate a promotion code. If your unit test genuinely tried to connect to a real database or a live external service for every check, it would become slow, unpredictable, and prone to failures unrelated to the code you're actually trying to test. What if the network is down? What if the database is overloaded? Your test would fail even if your discount calculation logic was perfect. This is precisely where test doubles come into play. The need for stand-ins. Think of test doubles like stand-ins, stunt doubles, or understudies in a play or a movie. When the main actor isn't available, or the shot is too dangerous, or you just need to rehearse a specific scene without the full cast and crew, you bring in a substitute. This substitute mimics the behavior of the real actor just enough for the scene to proceed. In software, test doubles are simplified, controlled versions of your code's dependencies. They allow you to isolate the unit you're testing, providing predictable responses from its collaborators so you can focus on verifying its specific logic. There are several types of test doubles, each serving a slightly different purpose. The most common and essential ones you'll encounter are stubs and mocks. The stub, a pre-programmed responder. Imagine you're developing a feature that sends an email notification to customers after their order ships. Your shipping notifier unit needs to interact with an email sender service. During your unit test for the shipping notifier, you don't actually want to send a real email, which would be slow, involve the internet, and annoy your customers during testing. A stub is a test double that simply provides pre-programmed answers to method calls made during a test. It's like an automated answering machine that you've recorded specific messages for. How it works. You configure the stub before the test runs. You might tell it, when the shipping notifier asks me, the email sender stub, to send an email, just pretend it worked and return true or no error. The stub doesn't do anything real. It just hands back the prearranged response. Purpose: to control the inputs to the unit under test. If the shipping notifier expects a certain response from the email sender to proceed, The stub provides that response without any external side effects. So, when you test your shipping notifier, you replace the real email sender with an email sender stub. Your test now runs quickly and reliably, verifying that your notifier correctly attempts to send an email and handles the stubbed response without ever touching a real email server. The mock, a behavior verifier. Now, let's say you're testing a order processor unit. This unit not only needs to get data from a customer repository, which would be a good candidate for a stub to return customer data, but it also needs to make sure that a logger service is called with a specific error message if the order fails. Here, you're not just interested in the return value from the logger. You want to verify that the order processor interacted with the logger in a particular way. A mock is a more dynamic test double that allows you to verify interactions between objects. It's like a stage director who not only cues an actor to say a line, like a stub, but also meticulously checks whether the actor delivered the line exactly as scripted, at the right time, and with the correct props. How it works. You program the mock with expectations up front. You might tell it, I expect the order processor unit to call my logerror method exactly once with the argument invalid order data. After the unit under test has run, you then ask the mock, were all your expectations met? The mock reports back whether the anticipated interactions occurred. Purpose: to verify that the unit under test called its dependencies as expected, with the correct data and at the correct times. Mocks focus on verifying outputs in terms of method calls to dependencies, rather than just return values. So, using a mock in your order processor test, you can confirm that when an invalid order comes in, the order processor correctly attempts to log an error message without setting up a real logging system. Other test doubles, briefly. While stubs and mocks are your workhorses, you might also hear about fakes. These are lightweight working implementations of a dependency suitable for tests. For example, an in-memory database that behaves like a real database but doesn't write to disk. They're more complex than stubs, but simpler than the real thing. Spies. These are like stubs or mocks that wrap around real objects. They allow you to call the real method of an object, but also spy on its interactions, recording what happened. Test doubles in good design, a symbiotic relationship. The forced use of test doubles in TDD is a powerful driver for good code design. If you find it incredibly difficult to create a test double for a dependency, it's a giant red flag. It often means your code is too tightly coupled. Your unit is so intertwined with its dependencies that you can't easily swap them out. This makes your code rigid and hard to change. Not following interfaces. If your unit directly depends on concrete classes rather than abstract interfaces, it's harder to substitute a test double. Designing to interfaces makes your code much more flexible. Difficult to isolate. Your unit might be doing too much, or its responsibilities are unclear, making it hard to test any single part independently. TDD, by compelling you to consider testability from the outset, leads you naturally towards a more modular, loosely coupled architecture. When you design your code so that dependencies can be easily swapped out for test doubles, you're building a system that is inherently more flexible, maintainable, and robust. Understanding and effectively using test doubles is a critical skill for any developer practicing TDD. It's what allows your unit tests to remain fast, focused, and reliable, thereby preserving the rapid feedback loop that lies at the heart of the TDD rhythm. With test doubles in your arsenal, you can test even the most complex logic with confidence, knowing you're verifying your code, not the health of an external system. Next, we'll shift our focus from these isolated test scenarios to how TDD fits into the broader, often messy, real world of software development. 8. TDD in the wild. Adapting to real-world scenarios. We've covered the core principles of TDD, from its rhythmic Red-Green-Refactor cycle to its power as a design tool and the crucial role of test doubles for isolation. This conceptual foundation is vital, but the real world of software development often presents complexities that can make applying TDD feel daunting. How does TDD fare when faced with existing codebases, external services, or the demands of a busy team? The good news is that TDD is remarkably adaptable. It's not a rigid dogma, but a flexible discipline that can be tailored to various real-world scenarios. The key is understanding how to apply its principles, rather than blindly following a prescriptive rulebook. The testing pyramid, knowing where TDD fits. One of the most important conceptual frameworks for understanding TDD's place in real-world testing is the testing pyramid. Coined by Mike Cohn, this visual metaphor describes a hierarchy of tests that collectively ensure software quality. At the bottom, unit tests, TDD's primary domain. Volume, many tests, speed, fast, cost of failure. Low, caught early. Purpose, verify the smallest isolated units of code. These are the tests TDD primarily focuses on creating. They are cheap to write, run in milliseconds, and pinpoint failures precisely. In the middle, integration tests. Volume, fewer than unit tests. Speed, moderate. Cost of failure, medium. Purpose, verify that different components or services work together correctly. This might involve testing interactions with real databases, external APIs, or other system services. While TDD focuses on unit tests, a well-designed, TDD-driven unit often makes integration testing easier because individual components are well-isolated and reusable. At the top, end-to-end E2E or UI tests. Volume, fewest tests. Speed, slow. Cost of failure, high, discovered late, harder to diagnose. Purpose, simulate actual user interactions with the complete system, e.g., clicking buttons, entering data, navigating pages. These are crucial for overall confidence, but are the most expensive and brittle. The pyramid illustrates a crucial point. You want many fast, cheap unit tests, fewer integration tests, and very few slow, expensive end-to-end tests. TDD helps you build that solid, broad base of unit tests, which catches the vast majority of defects early and gives you confidence to proceed. Relying too heavily on E2E tests, an ice cream cone anti-pattern leads to slow feedback, brittle tests, and high costs. Dealing with external dependencies, beyond unit tests. Chapter 7 introduced test doubles for isolating units. But what about when you do want to test against a real database or external API? The integration test layer. This is where you write your integration tests. These tests are not typically driven by the TDD cycle in the same way unit tests are. You usually write the code that uses the external dependency first, driven by unit tests that use test doubles, and then write separate integration tests to confirm the real dependency works as expected. Controlled environments. For integration tests, consider using lightweight, controlled environments. For databases, this might mean a small in-memory database or a dedicated test schema that can be easily reset. For external APIs, consider using a local test instance of the API or a service virtualization tool that can simulate its behavior. Focus on the seams. Identify the seams in your application where it interacts with external systems. Your unit tests will verify your internal logic around these seams, and your integration tests will verify the actual interaction at the seams. TDD and asynchronous operations. Modern applications often involve asynchronous operations, making network requests, processing messages queues, or handling callbacks. Testing these can be tricky. Don't test the waiting. Your unit tests should primarily test the logic that initiates the asynchronous operation and the logic that handles its completion. You generally don't want your unit tests to literally wait for network calls or message queue processing. Control time. For situations that involve time-dependent logic, e.g., waiting for a timeout, use test utilities that allow you to fast-forward time within your tests. These are conceptual time travel devices that simulate the passage of time without actually pausing your test runner. Mock callbacks promises. Similar to how you use test doubles for objects, you can use them to simulate the resolution of asynchronous calls. If your code expects a callback when a network request completes, your test double can immediately invoke that callback with a predefined success or failure response. These are sometimes called fake futures or mock promises. BDD and TDD, complementary approaches. You might also encounter behavior-driven development, BDD. BDD is an agile software development process that encourages collaboration among developers, quality assurance, and non-technical participants. e.g., product owners. It defines tests in a human-readable format, often using a given-when-then structure. BDDS focus. BDD focuses on the behavior of the system from the user's perspective. It helps ensure that everyone understands what the software should do and why. TDDS role. TDD can be seen as an implementation detail of BDD. Once a behavior is specified in BDD's human-readable format, e.g., given a user is logged in, when they click Buy Now, then their order should be processed. A developer would then use TDD to implement the underlying code, driving out the unit tests that ensure that specific behavior is met. Complementary. TDD helps you build the internal quality of your components, while BDD helps ensure you're building the right components that meet business needs. They work extremely well together. BDD clarifies the what, and TDD clarifies the how. TDD on a team, cultivating the culture. Implementing TDD successfully on a team isn't just about individual skill. It's about cultural adoption. Pair programming, a powerful technique to spread TDD knowledge and ensure adherence to the cycle. One person writes the failing test, the other makes it pass, and then they switch for refactoring, fostering shared understanding and quality. Code reviews ensure that tests are being written first. Look for tests that explain the intended behavior. Continuous integration, CI, automate the running of your full test suite, unit, and integration whenever code is committed. This ensures that the safety net is always active and catching regressions early. Education and mentorship provide training and support for team members new to TDD. Demonstrate its benefits and help overcome initial resistance. TDD is a skill that improves with practice, often feeling awkward at first. It requires a commitment to discipline and a willingness to think differently about developing software. When adopted well, it becomes an indispensable part of a team's workflow, leading to higher quality, faster delivery, and a more confident development process. In the next chapter, we will delve into one of the most challenging, yet rewarding, applications of TDD. Tackling existing, often complex and untestable, legacy codebases. This is where the safety net truly proves its worth. 9. The Legacy Code Challenge, TDD to the rescue. We've championed TDD as a tool for building new, well-designed, and robust software from the ground up. But what about the vast majority of software development, which isn't about starting fresh, but rather about maintaining, extending, or fixing existing systems? Enter the beast often referred to as legacy code. Legacy code, as famously defined by Michael Feathers, is simply code without tests. It might not be old, poorly written, or even difficult to understand. Its defining characteristic is the absence of an automated safety net. This lack of tests makes modifying it terrifying, refactoring it risky, and extending it often leads to new bugs. You touch one part, and something seemingly unrelated breaks elsewhere. It's the ultimate fear of change scenario. So, how can you apply the principles of TDD to a codebase where tests are almost entirely absent? The Red-Green-Refactor cycle, specifically the red, failing test, and green, make it pass phases, seems predicated on writing code that doesn't exist yet. This is where TDD's guardian angel role becomes paramount. The Boy Scout rule and incremental improvement. Before diving into techniques, let's internalize a guiding philosophy, the Boy Scout rule. This rule states, always leave the campground cleaner than you found it. In software, this translates to, always leave the code you're modifying a little better than you found it. When working with legacy code, your goal isn't to rewrite the entire system with TDD overnight. That's usually an impossible and dangerous endeavor. Instead, focus on small, incremental improvements. Every time you touch a piece of code to fix a bug, add a feature, or refactor, strive to add a small test around it, ideally introducing TDD principles into that micro area. Step 1. Finding a seam. To introduce TDD to legacy code, you first need to find a seam. A seam is a place in the code where you can change behavior without editing the code directly. It's often an interface where you can insert an abstract class or a testable subclass, or a point where dependencies can be injected or separated. The problem? Legacy code often has long methods, deep call chains, and hidden dependencies that are tightly coupled together. This makes it hard to isolate and test small units. The goal: locate the piece of code you need to change or the bug you need to fix. Then, identify the smallest possible point of interaction that you can cut or wrap to bring it under test control. Step 2, getting the code under test, gut. This is the most critical and often challenging step. Before you can apply any TDD, you must get the existing, untested code into a test harness. This often involves a process called characterization testing or learning tests. Write a characterization test, RED. Find the exact piece of legacy code you need to modify. Write a test that currently fails because it relies on the behavior of this legacy code, but it reproduces some known behavior of the existing code, e.g., if you call this function with these inputs, it should produce this specific output, even if that output is currently incorrect or undefined. This isn't yet about new functionality or bug fixes. It's about capturing the current behavior as it stands. Make it pass, green, run the test. It should fail. Now, you might need to make some small, safe refactorings to the legacy code, often called refactoring for testability, simply to make it possible to test it. These refactorings are designed to break dependencies or create seams so your test harness can interact with the code. Often this involves extracting method class, pulling out a long block of code into its own method or class, making it easier to isolate. Introducing an interface dependency injection. If a class directly instantiates a complex collaborator, e.g., new database connector, you might refactor it to accept that collaborator as an argument dependency injection, allowing you to pass in a test double. Wrapping untestable code. If a piece of code is inherently untestable, e.g., directly accessing a global static context, you might wrap it in a new, testable class that delegates to the untestable part. As you make these small refactorings, run your existing tests frequently, even if there's only one characterization test so far, to ensure you haven't broken anything. The goal is to get that characterization test to pass, reflecting the current, existing behavior of the legacy code. Once your characterization tests are passing, you have a safety net, albeit a small one around the piece of legacy code you intend to modify. You now know that any unintended changes will cause this test to fail. Step 3. Implement change with full TDD, Red-Green-Refactor. Now that you have your small safety net, you can proceed with the actual change you intended, whether it's fixing a bug or adding a new feature, using the full TDD cycle you've learned. New failing test, red. Write a new test that describes the desired new behavior or the correct bug fix. This test must fail. Make it pass, green. Write the minimal amount of code to make this new test pass. This might involve modifying the existing legacy code. Refactor, green. With all tests, characterization tests, and your new feature bug fix test, passing, refactor the code to improve its design. Remove duplication, improve naming, make it more readable. Your characterization tests protect you from breaking the old behavior, and your new test protects you from breaking the new behavior. The strangler fig pattern. A long-term strategy. For larger, more complex legacy systems, a technique called the strangler fig application, coined by Martin Fowler, can be highly effective. This involves wrap the old system. Create a new, modern application that gradually takes over the functionality of the old system. Build new features with TDD. Any new functionality is built entirely using TDD as part of the new system. Migrate piece by piece. Existing functionality from the old system is migrated piecemeal into the new system, driven by tests. The new system essentially strangles the old one by gradually replacing its functionality. This is a long-term strategy, but it allows teams to start applying TDD immediately to new development while chipping away at the technical debt of the old system in a controlled manner. The value of the safety net. Working with legacy code is daunting because the absence of tests makes every change a gamble. TDD, by forcing you to introduce characterization tests first, gives you back control. It's like entering a dark, unknown room and being given a flashlight. You can now see just enough to take the next small step safely. It's not easy, and it requires discipline. But the alternative, building on a fragile foundation without confidence, is far more costly in the long run. Embracing TDD, even in the messy world of legacy code, transforms fear into a methodical, controlled process of continuous improvement. With a solid understanding of how TDD can guide design, provide a safety net, and even tame legacy beasts, we're ready to address some of the common misconceptions and difficulties that developers often encounter when adopting TDD. In the next chapter, we'll navigate these common pitfalls and equip you with strategies to overcome them. 10. Common pitfalls and how to navigate them. By now, you should have a solid grasp of what test-driven development is, its profound benefits, and how it can be applied even in challenging situations like legacy code. However, like any powerful tool or discipline, TDD comes with its own set of common pitfalls and misconceptions. Failing to recognize and address these can lead to frustration, slower adoption, or even abandonment of the practice. This chapter will guide you through the most frequent stumbling blocks and equip you with strategies to navigate them successfully on your TDD journey. Pitfall 1. TDD slows me down. This is by far the most common initial complaint from developers adopting TDD. The immediate feeling is that writing tests before code and constantly switching context between tests and implementation is an additional overhead that reduces productivity. How to navigate? Trust the long game. Remind yourself that TDD is an investment. While the initial sprint might feel slower, the total time to deliver a high-quality, maintainable, and bug-free feature is almost always reduced. Less time spent debugging, less time spent refactoring, less time fixing regressions, and less time documenting. Practice short cycles. The key to TDD's efficiency is short, rapid Red-Green-Refactor cycles. If your cycles are taking more than a few minutes, you're either writing too much test at once or attempting too much implementation. Focus on truly minimal steps. With practice, these cycles become almost subconscious. Measure true productivity. Focus on delivered value or shipped features with confidence rather than lines of code written. TDD helps ship correct code faster. Pitfall 2. Overtesting or testing trivial code. Some developers new to TDD can become overly zealous, writing tests for every getter, setter, or incredibly simple method, believing more tests are always better. This can lead to brittle tests that break for no functional reason when code changes, and a perception that TDD is about achieving 100% code coverage. How to navigate? Focus on behavior, not implementation. Remember that TDD's primary goal is to drive design and specify behavior. If a piece of code's behavior is trivial and fully covered by testing a larger, more complex unit that uses it, then a dedicated test for that trivial piece might be unnecessary. Tests for value. Ask yourself, does this test verify a meaningful behavior or protect against a likely regression? If the answer is no, reconsider. Coverage as a metric, not a goal. Code coverage is a useful metric to find uncovered areas, but it's not a goal in itself. High coverage with poor tests is worse than lower coverage with good, meaningful tests. The focus should be on critical behaviors. Pitfall 3. Brittle tests. Brittle tests are tests that break easily, not because the underlying code's behavior has changed, but because its implementation has changed. They are highly coupled to the internal workings of the code under test. How to navigate? Test public APIs, not privates. Unit tests should primarily interact with the public interface of the unit under test, its public methods or functions. Avoid testing private methods directly, as these are implementation details that are likely to change during refactoring. Refactor tests too. Tests are code too. If your production code needs refactoring, your test code might also need it. Keep your test code clean, readable, and maintainable. Use proper test doubles. Overmocking or mocking too many parts of an interaction can lead to brittle tests. Understand the difference between stubs for state-based verification and mocks for interaction-based verification. Use them judiciously. Pitfall 4. Mismanaging dependencies, ignoring test doubles. Trying to test complex code without isolating dependencies properly, or without using test doubles, leads to slow, unreliable tests that are hard to debug. How to navigate? Embrace dependency injection. Design your code to allow dependencies to be easily injected, passed in, rather than hard-coded. This makes them easy to replace with test doubles during testing. Identify seams. For legacy code or complex services, identify the seams where you can introduce test doubles or extract testable components. Learn your framework's mocking capabilities. Most modern unit testing frameworks have built-in or pluggable libraries for creating and managing test doubles effectively. Invest time in learning these. Pitfall 5. Ignoring the refactor phase. It's tempting, especially when pressed for time, to skip the refactor step of the red-green-refactor cycle. You get to green, and you just want to move on. This is a critical mistake. How to navigate. Understand its importance. The refactor phase is where TDD delivers its design benefits. Without it, you're just doing test-first development, not test-driven development. You'll end up with passing tests, but a poorly designed code base. Discipline and team culture. Make refactoring a non-negotiable part of your workflow. Encourage it during code reviews. Allocate time for it. Small, frequent refactoring. Don't wait for a huge refactoring task. Do small, continuous refactorings after every green phase. This keeps the codebase clean incrementally rather than letting technical debt pile up. Pitfall 6. Over-reliance on TDD for all testing needs. Believing that TDD, or unit tests, are the only kind of testing you need. This leads to gaps in your testing strategy for integration, performance, security, or user experience. How to navigate. Understand the testing pyramid. As discussed earlier, unit tests, driven by TDD, form the base, but you still need integration tests for component interaction and a few end-to-end tests for user workflows. Complementary tools. TDD focuses on the internal quality and behavior of microunits. Other testing, methodologies, and tools are needed for broader system verification. Pitfall 7. Getting bogged down by TDD purity. Sometimes, developers get stuck trying to apply TDD strictly in situations where it's genuinely difficult or impractical. This can lead to analysis paralysis or frustration. How to navigate. Pragmatism over purity. TDD is a guide, not a religion. There will be times when applying pure TDD is challenging, e.g., highly volatile external APIs, complex UI interactions. In these cases, be pragmatic. You might write the code first and then immediately write the test, or focus only on the core logic with TDD and test the hard parts with other methods. Experiment and adapt. The best way to use TDD is the way that works best for your team and your project. Experiment, learn from mistakes, and adapt your approach. Navigating these pitfalls requires continuous learning, discipline, and a willingness to reflect on your process. TDD is a skill that improves with conscious practice. By understanding these common challenges and employing the strategies to overcome them, you'll ensure that TDD becomes a powerful asset in your development arsenal, leading to more confident and higher quality code. In our penultimate chapter, we'll place TDD into the larger context of a holistic testing strategy, emphasizing its role within the broader testing pyramid. 11. Beyond unit tests. TDD's place in the broader testing pyramid. Throughout this book, we focused almost exclusively on test-driven development and its primary output, unit tests. We've seen how TDD shapes design, provides a safety net, and allows for confident refactoring. However, it's crucial to understand that TDD is not the only form of testing, nor does it guarantee a bug-free system on its own. It's a foundational practice that contributes to a larger, more comprehensive quality assurance strategy. To truly build confident code, we must understand where TDD's unit tests fit within the landscape of software testing. This brings us back to the testing pyramid, a concept we briefly introduced earlier. Let's delve deeper into it to clarify the complementary roles of different test types. The foundation. Unit tests, TDD's domain. Characteristics. These are the smallest, fastest, and most numerous tests. They isolate and verify individual functions, methods, or classes in isolation from external dependencies, using test doubles as needed. Purpose: to confirm that each tiny component of your application works exactly as intended, fulfilling its single responsibility. They are excellent for guiding design, providing immediate feedback, protecting against regressions during refactoring, and serving as executable specifications. TDD's contribution. TDD is the engine for generating these tests. By writing tests before the code, you create a robust suite of unit tests almost as a byproduct of your development process. This ensures maximum coverage at the lowest level of granularity. Without a strong base of unit tests, you're building on shaky ground. Any issues at this foundational level will propagate upwards, becoming harder and more costly to detect and fix later. The middle layer, integration tests. Characteristics. Fewer in number than unit tests, these tests verify that different components or services work correctly when integrated. They might involve real databases, file systems, external APIs, or message queues. They are slower than unit tests but faster than end-to-end tests. Purpose: to confirm the correct interaction and data flow between modules, services, or layers of your application. They ensure that your separate, unit-tested components can talk to each other properly, and that the real-world interactions, e.g., saving data to a database, making a network call, behave as expected. TDD's contribution. While TDD primarily drives unit tests, the good design practices it enforces, e.g., loose coupling, clear interfaces, dependency injection, make it significantly easier to write effective integration tests. If your components are modular and have well-defined interfaces, you can more easily set up and isolate the specific interactions you want to test in an integration scenario. Think of it like building an engine. Unit tests ensure each piston, valve, and spark plug functions individually. Integration tests ensure that when assembled, the pistons move correctly with the crankshaft, the valves open and close on time, and the spark plugs fire at the right moment, allowing the engine to turn over. The Apex end-to-end E2E/UI tests. Characteristics. These are the largest, slowest, and least numerous tests. They simulate real user behavior by navigating through the entire application, often via its user interface, UI. They touch all layers of the system. Purpose: to provide a high-level confidence check that the entire system works correctly from an end user's perspective. They verify critical user journeys and business workflows. TDD's contribution. TDD's strong foundation of unit and integration tests reduces the need for a vast number of E2E tests. Because you've already verified the internals and the interactions, your E2E tests can focus on the critical paths only, rather than trying to also catch errors that should have been caught much earlier and cheaper by unit tests. If your unit tests are solid, an E2E test failing means either a crucial integration point broke or the UI itself isn't rendering or interacting correctly. It also means you have a much smaller area to debug, since you know the lower layers are likely working. Continuing the engine analogy, the E2E test would be starting the engine and making sure the car actually drives. You don't need 1,000 car drives tests if you know your engine works, your transmission works, and your wheels spin, etc. You just need to confirm the final outcome. Beyond the pyramid. Other specialized testing. The testing pyramid focuses on functional aspects, but a complete quality strategy involves other forms of testing. Performance testing. How fast does the application run under load? How many users can it handle? Security testing. Is the application vulnerable to attacks? Usability testing. Is the application user-friendly? Accessibility testing. Can users with disabilities use the application effectively? Exploratory testing. Manual, ad hoc testing to discover unexpected behaviors or edge cases. These are not directly driven by TDD, but a TDD-enabled codebase often makes them easier to conduct. A well-designed, modular system that lends itself to unit testing is typically easier to instrument for performance monitoring or to audit for security vulnerabilities. The synergy of a holistic strategy. The power of TDD isn't that it eliminates all other testing. It's that it shifts the quality paradigm left, meaning issues are identified and addressed as early as possible in the development lifecycle. Earlier feedback. Unit tests, TDD, give you feedback in seconds. Integration tests in minutes. E2E tests in minutes to hours. Catching a bug during unit testing is orders of magnitude cheaper and faster than catching it in production. Reduced debugging. Because unit tests pass, if an integration test fails, you know the problem is likely at the integration point, not deep within a component. This narrows down the search considerably. Maintainable tests. When unit tests are comprehensive, higher-level tests can be simpler and more focused, making them easier to maintain. In essence, TDD builds a rock-solid foundation of confidence at the granular level. This confidence then radiates upwards, allowing you to build fewer, but more meaningful, higher-level tests. It's like building a skyscraper. You meticulously inspect every single beam, unit test, ensure the connections between them are strong integration test, and then perform a final structural integrity check on the completed building ETWI test. You wouldn't skip inspecting the beams and just hope the skyscraper stands. By understanding TDD's vital role within this broader testing ecosystem, you can craft a comprehensive quality strategy that maximizes efficiency, minimizes bugs, and delivers truly confident code. You're not just writing tests, you're building a fortress of quality, brick by brick, with TDD ensuring each brick is perfectly formed. In our final chapter, we'll reflect on your TDD journey and discuss how to continue on the path to mastery. 12. Your TDD journey, continuing the path to mastery. Congratulations! You have journeyed through the core principles of test-driven development, explored its profound impact on software design, embraced the comfort of its safety net, and learned how to navigate common pitfalls and integrate it into a broader testing strategy. This book has aimed to demystify TDD, revealing it not as a complex academic discipline, but as a pragmatic and powerful process for building software with confidence. You now understand that TDD is far more than just writing tests. It is a disciplined approach to development that compels clear thinking, drives good design, and provides immediate, invaluable feedback. It has the power to transform the often stressful act of software creation into a more deliberate, enjoyable, and ultimately, more successful endeavor. Recapping the core. Your TDD toolbelt. Let's briefly revisit the key takeaways from our exploration. The RGR rhythm, Red-Green-Refactor. This rapid, iterative cycle is the heartbeat of TDD. It defines your workflow, ensuring you always know your next small step and builds confidence with every passing test. TDD as a design tool. By writing tests first, you are forced to consider the desired behavior and public interface of your code before implementation. This inherently encourages modularity, loose coupling, and simplicity hallmarks of quality software design. The safety net. Your growing suite of unit tests acts as an automated regression detection system, giving you the courage to refactor aggressively, introduce new features, and tackle legacy code without fear of breaking existing functionality. Handling dependencies. Test doubles, stubs, mocks, fakes are crucial for isolating your unit tests from external systems like databases, networks, and third-party services, ensuring your tests remain fast, reliable, and focused. Real-world adaptability. TDD isn't an all-or-nothing proposition. It fits seamlessly into the broader testing pyramid, complementing integration and ETWI tests, and can be pragmatically applied even to challenging legacy codebases. Navigating pitfalls. You're now aware of common misconceptions and challenges, like the feeling that TDD slows you down or the risk of brittle tests. Understanding these helps you anticipate and overcome them. Mastery is a journey, not a destination. While you now possess a strong theoretical and conceptual understanding of TDD, true mastery, like any skill, comes through consistent, deliberate practice. Embrace the awkward phase. Your first few attempts at applying TDD might feel clunky, slower than your usual pace, or even frustrating. This is completely normal. Keep at it. Just as learning to ride a bicycle involves wobbles and falls, learning TDD involves moments of awkwardness. Start small. Don't try to TDD your next massive project all at once. Pick a small, isolated module or even just a single function and apply the full Red-Green-Refactor cycle. Build up your confidence incrementally. Practice consistently. Like a musician practicing scales or an athlete honing their technique, the Red-Green-Refactor cycle needs to be practiced daily. Make it a habit. Reflect and improve. After a coding session, take a moment to reflect. How did your tests guide your design? Were they clear? Did you refactor aggressively enough? What could you do better next time? Continuing your TDD journey. Your learning doesn't stop here. The world of software development is constantly evolving, and so too are the nuances and best practices surrounding TDD. Here are some avenues for continued growth. Read more. Explore other foundational texts on TDD, clean code, and software design. Dive into specific TDD patterns or advanced test double techniques. Look up articles and blogs from experienced practitioners. Join the community. Engage with other developers. Participate in online forums, attend local meetups, or join communities dedicated to TDD and quality software. Learn from others' experiences, share your own, and ask questions. Experiment with different languages, frameworks. Apply TDD in a new programming language or with a different testing framework. The core principles remain the same, but you'll gain a deeper understanding of their universality. Pair program. If possible, find a colleague who practices or wants to learn TDD and pair program often. This is one of the most effective ways to learn and reinforce the TDD rhythm and design principles. Teach and mentor. The best way to solidify your understanding is to teach others. Explaining TDD to a new colleague or contributing to a learning resource will deepen your own knowledge considerably. The power of confident code. Ultimately, your commitment to test-driven development is a commitment to quality, discipline, and continuous improvement. It's about taking ownership of your code, reducing the fear of change, and building software that is not just functional, but truly robust, maintainable, and adaptable. You are no longer just writing lines of code. You are building systems with intent, with clarity, and with a safety net that empowers you to create with unparalleled confidence. This journey to mastery will make you not just a better coder, but a more confident, valuable, and respected software engineer. The quest for confident code is an ongoing adventure. Go forth, write your tests, and build amazing things. Your code and your future self will thank you for it.